This is also a microphone. Learning theory. So what is the complexity of a function class? So when we do machine learning, we have some function class that we choose a function from based on empirical data. We want this function to be such that it has a small risk. Small risk means we have some loss function. We compute the expectation of that loss function over an unknown but fixed distribution, which generates both training and test data. We want the expectation of that loss function to be small. So from our class of functions, we want to choose a function such that this expectation is as small as possible. It turns out that this is not trivial. We can't simply choose the function based on which one has the lowest training error unless some other conditions are satisfied. And these conditions are related to complexity of function classes. So it turns out if we have, maybe a bit low, if we have a function class whose VC dimension is finite, then we will in the limit always be able to be consistent, so to get a risk which is as low as the lowest possible risk in our function class. VC dimension was one of the capacity concepts, maybe the simplest one. It's just a single number that characterizes a class of functions or a learning machine. It's the single number that characterizes starting from which number of observations the learning machine no longer has full complexity or full capacity. So up to a number of observations which equals the VC dimension, the learning machine or the class of functions is as complicated as it could be, so it can realize all possible separations between the data, and afterwards it can't anymore. And if we can explain our data, if we can explain a large set of data with a learning machine that has a finite VC dimension, and VC dimension is even significantly smaller than the number of data points, then this cannot be chance, or it is unlikely to be chance that we can explain the data well, because we are working with a learning machine whose VC dimension is such that it usually cannot explain arbitrary large data sets. So that's the basic idea. And in the end, it comes down to finding good function classes if we want to learn well. And good means the complexity should be controlled. Ideally, we should be able to give some bounds on this complexity to understand what controls the complexity, how to algorithmically minimize it. And of course, it's not just about having small complexity, but at the same time, the function class should be able to explain real-world data. So it should be complex enough to model the kind of dependencies that we want to model in the real world. So that's a certain trade-off. And I started introducing these kernel function classes as nice examples where we can give bounds on the capacity. I'll say more about this later. Even though there are complex classes of functions, because they correspond to linear function classes in some other space, and we can do the theoretical analysis in that other space. So that was the basic idea. And then I showed you a few, I gave you a bit of an introduction to kernels and feature spaces. So I was saying we pre-process the data, and then we look at some examples where in the higher dimensional space we compute dot products, and we find out that they correspond to simple functions in the lower dimensional space, which we call kernels. So this was an example of a kernel. This kernel equals the dth power of the usual dot product taken in the input space, and it computes all possible products of d features of d coordinates in the high dimensional space. So it computes all possible products of d coordinates, and this constitutes the mapping into the higher dimensional space. What else did we look at? I mentioned Mercer's theorem. I mentioned the class of positive definite kernels. So these are these symmetric functions, two variables. I think now we have a better laser pointer. Functions of two variables, symmetric functions, such that if you compute the kernel matrix, which we get by only substituting the finite data set in here and here. This matrix is positive definite. This matrix is called the Gram matrix or kernel matrix. And we then, I think we also covered this bit, gave 2 examples of kernels, and I mentioned that kernels have this benefit that we can construct nonlinear algorithms from linear ones, and maybe even more importantly, we can apply linear methods to data that don't live in a vector space to begin with, as long as we can construct a kernel on this data. So we have some data which is from some arbitrary domain, maybe even just a set or a set of graphs or strings. As long as we are able to construct a similarity measure, K, or a kernel which satisfies these properties of positive definiteness, then we get a vector space representation of this data for free. Okay. So I was going to, today, my plan is to show you the feature map of a positive definite kernel, show you how to construct that. It's relatively elementary, and I was hoping that maybe also some of the parts we can do together, or you do some things, why not wait here and then we solve them together on the whiteboard. So let's see how it goes. This is, let me see, I think, yeah. Yeah. So I think these 2 cases are relatively simple, and maybe we can start with these 2. So I'm going to show you the definition again. Maybe you have them, you have it on the slides if you downloaded them. If not, I recommend that you briefly write it down. So a positive definite kernel is a kernel that's symmetric, and that has this property that for all xi, xm in x, and for all real numbers, this quantity here is non-negative. So if you want to, if you don't have it already, maybe briefly write this down. And I think we're not going to need this one down here now. Okay. Okay, so I'll move to this thing here. And now I would like you to try to prove, because usually when one sees a definition, one reads it, but maybe one doesn't understand the details before one has worked with it a bit. So I want you to work a bit with this definition, and I want you to first do these 2 things. One is, if we define a function of 2 arguments like this, where we assume that phi is a mapping from some non-empty set, calligraphic X, into a dot product space H. So we define the mapping like this. We don't claim it's positive definite kernel. Then from this definition, it already follows that this kernel is positive definite. So I want you to prove that this thing here satisfies the equation that's required, the inequality required for positive definite kernel. That's the first thing. And the second thing is, I would like you to also show that this thing here is a positive definite kernel. So what is this thing? It's a kernel defined on sets. A and B are arbitrary finite subsets of X, and the value of K is defined to be the sum over all elementary kernels. So we now assume that K is a positive definite kernel. So we take the sum over all these positive definite kernels over the sets A and B, and it turns out that this is again a positive definite kernel, this time on these finite subsets. So in the first one, we don't assume anything about K, we just assume that phi is such a mapping. In the second one, we assume that this small k is a positive definite kernel. So I'll give you a few minutes and try to play around with it, and I'm not going to force anyone to do it, but I will ask for volunteers at the end, if you want. just to check, how many have solved the first problem? Okay, so I'm not going to ask you to get up, so you can be open in your assessment. So I'll give you a bit more time, and I think we should actually do the second one a bit later, because if we have to prove it based on what you know already, it's a bit complicated, and later on it will be much easier. So just do the first one now, or the second one is optional if you want, you can try it. But I'll give you a bit more time to do the first one until at least half of you have done it.
Can you go back to the previous slide?
Yeah.
No, I mean to the slide where you find.
How many of you have solved the first one? And who would like to have some more time? Okay, let's get on. Yeah. Okay. So, is there anyone who is relatively confident that he or she has found a solution?
So you just apply the definition and then use linearity to the sums inside the inner product. And then
Right. So you apply the definition, substitute this form of the kernel, right? Right. And then you use linearity. So linearity means you can take these coefficients inside the sum. It also means you can take the sums, inside the dot product. It also means you can take the sums into the dot product. So let's do both at the same time. Okay, and then? And that's because, so this vector here, let's call this V. That's the same vector. Doesn't matter that we use a different index. So this is a dot product of some vector with itself. And then that's not negative. So is it clear to everybody?
So actually, could you if you just absorb AI and AJ into the dot product, and then since the dot product is always positive, just sum positive dot product.
So you're saying we only put this and this inside, but we need the sums outside?
Yeah.
Something like this. Well, it turns out that not all these terms will be positive, because this is not the same as this, not necessarily, right? That the terms if I equals j, they will be positive, the other one's not. And so when you sum them all up, they will be positive, but some of them might well be negative. Okay, thank you very much. So let's we skip the second one because it would be too complicated now, but later on it would be very easy.
I have a question.
Yes.
On the definition of the kernel, K x prime equals to the dot product between phi x and phi x prime x.
Yeah.
The phi x is a function of x, and the phi x prime is a function of x prime.
That's right.
So how do you define the dot product between two functions?
Oh, okay. So the question is, he says phi is a function of x and or phi of x prime is a function of x prime, so they're both functions, well, or they are elements of a Hilbert space, right? Question how to define a dot product in the Hilbert space. It depends what kind of objects they are. So a Hilbert space, by definition, is a vector space with a dot product, which is complete in a certain sense. But so you can define dot products for functions. You can define dot product for vectors. For functions, a typical dot product, for instance, is the integral over the product of two functions. But in a reproducing kernel Hilbert space, which is what we're dealing with today, it will be a little bit different. So maybe just for now, just think of it abstractly. Dot product is just is a symmetric bilinear form with certain properties. Yeah, I don't know how to answer that better. So it's just the dot product is just a certain mathematical object in certain type of vector space, actually in a Hilbert space or pre-Hilbert space if it's not complete. And this mapping phi could go into a space of functions, but it could also be a mapping into a vector space if you prefer to think of it as a vector space, and then you use a normal dot product. Yeah. Any more questions about this? So yeah, so I assume Hilbert spaces are. This is something that maybe the physicists normally will be familiar with, and for the computer scientists, maybe it will initially be a bit scary to have these spaces that could be potentially infinite dimensional. But the Hilbert spaces are mathematically very nice objects, very well behaved, and usually most of the things that work in normal Euclidean vector spaces also work in Hilbert spaces. Okay, so let's move to a few more properties. So basically, my goal now is. So we've seen that this is true, the first of these two statements, and I basically want to prove the converse, by which I mean the following. If we have some positive definite kernel, so a kernel that satisfies this property here, down here, where's my laser pointer? Kernel that satisfies this thing, then there exists some mapping phi and some space h with the dot product that phi maps into, such that the kernel can be written in this form. So this means everything that has this form is a positive definite kernel, and every positive definite kernel actually has that form or can be given that form. Not necessarily with a unique phi, but there is some phi such that the kernel can be written this form, and that's very nice because then we can basically think of the kernel as a dot product just somewhere else, and a lot of things become very, very nice and simple. For instance, this thing becomes very simple to prove. And since we're not going to use this one in constructing the converse of this, maybe we just skip it for now. So let's get the converse and then we'll see how it goes. Okay, so let's think of a few more properties. Maybe we don't have to prove all of them, but again, I would like you to play around a bit. And it's so this one maybe was the first one, and let's see. I think we try to prove this one as well, and this one, and this one. So let's actually, if you want, you can try all of them, but maybe down here it gets a bit more messy. So this one is relatively difficult. This one is maybe more for the mathematicians. This is easy, but so let's say try to do some of those up to here. To play a bit with the definition, and I have some hints here. Maybe for the first one I don't give you a hint. For the second one there's a hint written here. So the hint is that you have to write down the gram matrix. Remember the gram matrix or the kernel matrix is the matrix of the dot product between all training points. Here the training points are just x and x prime, so it's a 2 by 2 matrix. And then think about what properties does this matrix or determinant have in the case that the matrix is positive definite. Here the hint is you can prove this one by using this one, so you first prove this one, and these two are basically elementary by substituting into the definition. So I'll give you another few minutes and play around a bit with it, and then we'll see. I wonder if the video lectures are going to show my face for 5 minutes without any sound. Just checking that you don't follow me with the camera. directly at the table, you can ask Neil. He will come around and give you some assistance.
I've never invigilated an exam. I'm guessing this is what it feels like.
Well, actually, no. I had one before. I found the video of the Palma tsunami.
Really?
I could show it. Maybe I would scare some people.
Yeah, no, that'd be interesting.
This time, I'll show you.
I'm sure there's someone who actually experienced the tsunami in Japan. I think about that. That was on the sea thing, wasn't it? It must have been a big event. I mean, a big landslide. Similar thing to what they described. Easy, isn't it?
From here to here.
Alright.
Oh, wait, what is this?
This is mine.
It's leche.
Well, I don't know. That's cheating because they're giving me the leche separate. That's not the same, is it?
No.
I'm a little bit disappointed, to be honest. It's funny that they call this milk. It's condensed milk.
So maybe checking how many of you have solved 3 or more problems? How many have 2 or more? 1 or more? 0? 0 or more? You're not answering my questions. Okay, I'll give you 2 more minutes and then we'll do them here.
It's all the negative.
Okay, let's do the first one. You want to ask a question? Or you want to say again? K sub n. So K sub n, all of these K's are positive, K sub n are positive definite kernels. So that's the assumption. It's a sequence, so all of them are positive definite, and if the limit exists. But I mean, you don't have to prove this one. If you go up to here, that's enough. And we're not going to need these ones down here. So let's do the first one. The first one we're actually going to need. Someone have an idea how to do it? You can either do it here or just tell me and I'll do it. I'm sure some people have solved the first one.
Yeah, just by being the feature map.
Can you speak louder?
Take A to be a single one.
Yeah.
0 is not a variable.
Okay, so I think you're saying you want one of the A's to be 1 and everything else 0, or equivalently you could say you just want to take one data point, right? Because here we say that any, where's the laser pointer again? Any set of training points, so in particular it could be a set that only has one element. So let's do that. So we take only one element, so the sum goes only from 1 to 1. We can remove the sum. We only have one A, we set it to 1. So we get 1 times k of x1 is positive. So we're done. So the first one was easy. When it means that the diagonal elements of such a kernel, and of course also of a kernel matrix, are always non-negative. So if you have negative diagonal elements, you know it's not a positive definite kernel. So let's look at the second one, which is a generalization of a Cauchy-Schwarz inequality that you probably know from dot products. So any ideas how to prove the second one?
Matrix in the Hilbert space, then the ground matrix should be positive.
So there you construct the grammar matrix for which training points? X prime. Okay. So let's write down the grammar matrix. Okay, and now?
Grammar matrix is positive definite.
Okay, grammar matrix is positive definite.
The determinant is also positive definite. This also is positive.
It's not negative, right?
It's not negative.
Yeah. So the grammar matrix is positive definite in our notation, which still includes eigenvalue 0, therefore the determinant is non-negative. Let's write it like this: the determinant is non-negative, and then we calculate the determinant. So the determinant is this times this. Minus okay. Anything else? This is greater than 0. Now we have to use the fact that k is symmetric. So this is actually kx prime squared. And now if we take a sharp look at what we have here, it should be the same. So we move this to the other side, and we have the upper bound, which is this thing here. Okay? Any questions? So let's do the next one. Any ideas how to solve the next one?
Also from the determinant.
Also from the determinant. So you are you want to compute the determinant, or you want to, or do you want to use this one?
Yeah, we use the same.
You can use the same one, right? You can. So you can simply say, I write this one down. Well, or maybe I don't. Well, let's write it. So in the general case, we know that this is true now. Sorry. Yeah, we know that this is true. Now, if it's the case that k of x is 0 for all x, so in particular it's also 0 for x prime, doesn't matter anyway, this thing is 0. So we have an upper bound on a squared thing which is 0, therefore the thing itself is also 0. Okay, shall we do the other ones as well? Well, actually, I think we might not be using them, but they are relatively easy, so we can briefly do them. So alpha times k, how do we prove that?
Okay, isn't it easier to visualize all this geometrically in the RKHS?
Okay.
These follow directly without any determined considerations if we look at them as vectors in the RKHS.
Okay, so he's saying it's easier to do all this by visualizing them in the RKHS, and they follow directly. So for those of you who visualize well in the RKHS, maybe that's the easiest way. Only one note of caution: we haven't yet proven that there is the RKHS. I mean, so far these results we're just working with the properties of positive definiteness of the kernel, and we're going to use them to construct the RKHS. So it's nice to prove them by elementary means, what we know already, and then we can continue with the RKHS. But I agree, once we have the RKHS, many things become much easier to prove. Yeah. Okay, so this one, maybe it's too easy and you don't want to answer it. Any thoughts how to prove that? So you put it in. Right, yeah, so you have this, we have this condition. You know that this is positive. Therefore, we also know that this is positive if alpha is non-negative. Now let's move the alpha in here. Then we have our original formula again. And here we have alpha times. We know it's still positive. And what is this thing? This is actually the same as, maybe now this is like a mathematician would write it. This is kernel alpha times k evaluated at xj. So now we know alpha times k is a positive definite kernel. Okay, and basically k1 plus k2 works exactly the same, right? So this the sums is linear not only for products but also for sums. So we can do the same thing to prove that this is positive definite. This one is also relatively elementary. This one is the hardest one. If you want to play around with it, you can try tonight. This is essentially a result of Schur for positive definite matrices. So Schur proved that if you have two positive definite matrices of the same size, and you take the element-wise product, called star in MATLAB, and you get a positive definite matrix. So if you don't know that yet, it's a pretty surprising result. It's not trivial to prove, but it's also not impossible. I don't know the proof by heart, but it's maybe a page or something like that. So it can be done. So if you want to try, but we're not going to use it. And from that, you can also prove some results about tensor products and other things. But we won't need all of those. Okay, so any questions about this so far? So even if you haven't solved all of them, or even if you haven't solved a single one of them, if you have worked with the definition, then that was the purpose of the exercise. So you might remember this definition or what it's about. And now we will use some of these facts to construct the feature space. Okay, so the basic idea, this is the overview of this construction. It's an elementary construction. The basic idea is we have to define this feature map. So now we want to prove, given a positive definite kernel, there is a feature map such that the kernel is the dot product after the feature map. So we want to prove, given k, there is a map phi such that this equality is true. So let's define the map phi and then show that it does what we want to. So we have to define the map phi into some space. We have to construct a dot product in that space. So because we have to both define phi and the Hilbert space into which it goes. And then we have to show that that dot product together with that map phi satisfies this equality for our given kernel k. Okay, so we are going to actually use a space of functions like someone here in the back was mentioning before. So the way of constructing Hilbert spaces is to deal with spaces of functions. And the functions that we're going to use will be functions defined on this domain X, functions of one variable, which we get by taking the kernel and substituting X into the second, or the first, it's symmetric, doesn't matter, but let's say into the second argument of k. So now the first argument is still open, which is why this is a function on X. So it's a function and the argument of the function is plugged into here where the dot is written. And visually, for instance, you can imagine if we use a Gaussian kernel or a squared exponential kernel. Exponential squared, whatever. Exponentiated quadratics. So the Gaussian process, people have to have many words for Gaussian.
That's just my word.
So we were talking about this the other day, and it's like the Eskimos having lots of words for snow, or as Neil pointed out, like the Finnish having lots of different words for independent component analysis. So you take one of these kernels, you map into that space, and the image of a point X in that space of functions will be a Gaussian kernel centered on that point X. The image of a point X prime in that space will simply be a Gaussian kernel centered on X prime. So we have these different bumps. These are functions mapping X into R, right? Because whenever we put some X into them, they give us a real number. This is a compact notation for writing the space of all functions mapping X to R. So this is a mapping. We can do that. It's not yet into a vector space, but we can turn it into a vector space quite easily. We can then endow it with a dot product that satisfies this equality. That's the non-trivial step. That's the step where we're going to exploit the fact that k is positive definite. And the last step is actually, I will skip that step. That's sort of a mathematical detail. Okay. So the first thing is we have to turn it into a vector space or a linear space. And we simply do this by saying well, first of all, so I told you that these kinds of bumps, these individual things, they are elements of our space. They are images of input points under our feature map phi. We will simply declare that if we take sums of such bumps, and actually even if we multiply them with some real numbers before taking the sum, so if we take general linear combinations of such bumps, we will simply say these are also elements in our space. So that's the definition of our space. It contains all functions of this form that we get by taking these bumps and taking linear combinations. So typical functions of our space have this form like this, f or g. Okay? So you just stop me whenever you want to. So alpha, beta are real numbers. These are from our domain, and these are finite sums. Now we have to define a dot product on such functions. Well, we actually don't have much choice how we can define the dot product, because we want the dot product to be such that if we take two elementary bumps, just images of input points, we want that dot product to be equal to the kernel. So remember, we want this to be true. Now we have defined our mapping to take x into a kernel centered on x. So therefore we want this thing to be true here. So the dot product between k of x, k at x and k at x prime has to be equal this thing here. Therefore, for functions like this, in order to have a bilinear dot product, and dot products have to be bilinear, we have to define it like this. So we just have to take these coefficients that we have from the functions. So show you the functions again. So function f was an expansion in terms of the alphas and the x's, and g was in terms of the betas and x primes. So we have to also use that in our definition of this thing here, which we will show that it's a dot product, simply by having all alphas, betas, and here x prime. Okay, that's a definition, and by construction it's bilinear, it's symmetric because I can interchange alpha and beta, and I can interchange x and x prime because the kernel is symmetric. So this is so far what's called a symmetric bilinear form. There's a little detail, which is one has to prove that it's well defined. That's again maybe just for the mathematicians here. By this I mean the following. If we it's possible that the same function f could be possibly written in different ways using such an expansion, using different x's and different alphas. It turns out that this is quite not unusual. For kernels that are positive definite but not strictly positive definite, this will be the case. For kernels that are strictly positive definite, it turns out it's not the case. But anyway, in general, it might happen that functions can be written in different ways. And if we define this dot product, we want the value of the dot product to really be dependent only on f and g. It shouldn't depend on how we express f and g in terms of other functions. Question?
I was wondering, can you think of this kind of representation as, so when your f is basically a span of columns of the grand matrix K?
I'll get to that in a minute. So it's you can think.
Because I've seen it's very similar. So this space is basically the column space of the grand matrix.
So it's a bit like that, but it's in a sense it's like an infinite Gram matrix where, because what is this function? This function. I mean, actually this notation already denotes this is like a vector with the number of components of the vector is the cardinality of x. So this, you can think of this as a vector where you run through all possible things that you could plug into here. And if they're infinitely many, it's an infinitely large vector, and you get an infinitely large matrix. But basically the intuition is the right one. You know? But we will get to the finite case after this. But maybe for now, think of it as functions. Okay, so we want to show is well defined. We want to show that this is this value, this thing that we defined here, only depends on f and g, and it doesn't really depend on how we express f and g in terms of the alphas, betas, x primes. How do we see that? Actually, there's a very simple way to see this, and that's the following. We can notice, simply for a trivial identity, that this thing here can be rewritten in two different ways, like this and like this. Now remember G, just go go back for a second. G was an expansion in terms of the betas and x primes. So if you see here, the alphas are still there, the betas and x primes are in the G, so we still have the whole thing. And likewise, F was an expansion in terms of the alphas in the x's. So if you plug F in here, you also recover this. So these are just different ways of writing the same thing. And the nice thing about these two expressions is that from this expression, you can see that it doesn't explicitly depend on the betas and on the x primes. It only depends on the G that is formed by the betas and x primes. And likewise, this one shows that it doesn't depend on the alphas and the x's, which we use to express F. It only depends on F itself. So the overall thing doesn't depend on alpha, beta, x, and x prime. It only depends on those through F and G. So I hope I didn't say this in a confusing way. But I think if you're a mathematician and you're worried about things like well-definedness, you probably got it. And if not, you were probably not worried about it in the first place. Okay, so special cases. I've already told you one special case before. That's this special case here. So if we, if the dot product for the case where we simply plug two of our elementary functions, two of our kernels, was simply, well, I shouldn't call it dot product yet. So our bilinear form for these elementary functions was simply equal to the kernel evaluated at xx prime. This is the reason why this is sometimes called a reproducing kernel. When you put the kernel together with itself, you get the kernel again. And these spaces are called reproducing kernel Hilbert spaces. And another special case is if we use a general G, but a very simple F, then we go back to here. If you use a trivial F, then this alpha here collapses. The F, there's no alphas anymore. Only one of them is 1 and the rest is 0. So we only keep the G. So in that case, K together with G simply evaluates G at the point X. So this is a function G. This is the value of the function at the point X. So this means, in mathematical terms, people say the kernel represents point evaluation of functions. This is going to be a nice property because there are many Hilbert spaces of functions where point evaluation of functions is not possible. So for instance, if you have heard of things like L2 spaces, in an L2 space typically the actual elements of the space are equivalence classes of functions where if two functions differ only on sets of measure 0, they are considered to be the same function or they're in the same equivalence class. So in an L2 space normally it doesn't make sense to talk about values of functions at individual points in such a reproducing kernel Hilbert space as we are just defining them. It does make sense, and we even know there's a very simple operation to evaluate functions. So you could say that for machine learning this is good because after all we want to, if we talk about generalization, we talk about values of functions at points. So maybe it makes sense that we can talk about these are well-defined objects. And another way to think of it is that there's a famous theorem of linear algebra. No, it's not linear algebra. Functional analysis. The Ries representation theorem, which says that well, for our case here, it would say that. Well, it says every continuous linear form can be written as a dot product with some element here, and in our case this now means that point evaluation is continuous because here this says that point evaluation can be written as a dot product between an element that we want to evaluate and some other element. So this other element is also an element of our space. So this is a continuous operation here. Point evaluation is continuous, and that's you could also say it's kind of a topological prerequisite for generalization that point evaluation is a continuous operation, but that's just a side note. Okay. So now we show that this thing that we have defined, this bilinear form, is a positive definite kernel. So that's not what we wanted to show. We want to show in the end that it's the dot product. But first we'll show it's a positive definite kernel. And it's a positive definite kernel on a set of functions. So now the inputs to our kernel, to this kernel here, our functions. I mean, in the end, we want to define a dot product on functions. Now we first define a kernel on functions, and it's these kind of functions, like the functions that we had before. How do we show this? Well, we have to look at this typical property of positive definite kernels and show that this property is satisfied. Okay, so let's look at this property. So we write down this quantity here. We already know that this thing here with the angular brackets is a symmetric bilinear form. So far, so much we know already. So we can use bilinearity. We can take this sum and the coefficients inside. So the first sum over I we take in here, and the gamma I, and this, everything with j we take in here, which gives us this. Now we observe that this quantity is again a function, is identical to this function here. So let's call the function f. Okay, so that's our definition of f. Now we know that we have a linear space. Linear spaces are in particularly closed under addition and taking linear combinations. Therefore, we know that this function here is again element of our space, and every element in our space can be written like this. So we write our function f like that. We don't know the coefficients, but we know they exist. The same function here again. Actually, I could have also written j here, and then I move the whole thing outside of this bilinear form again. So the coefficients and the sums, I'll take them out again. I'm left with the dot, or this bilinear form between this kernel and this kernel. And now we can use the reproducing property to combine these two kernels into one kernel. So the reproducing property was this thing here. We use that here. So we're left with this. We move this out. We move this out. We're left with this and this. Now think of this as an index j. So we get this here, and here we have everything here we have moved out. And now we use the fact that k was a positive definite kernel to begin with. So by definition of k, this is now negative. So since k is positive definite, we also know that this thing here is positive definite kernel. Okay, so that's the question so far. Yes?
The upper index m in the definition, the upper index m.
Can you speak louder?
Yeah, the upper index m.
The upper index.
So has it anything to do with the number of training examples and which you?
No. I mean, there's no training yet. We just look at data points. So this is just an arbitrary. I should have written m element n. So all these functions that we can write with finite m in this form. Yeah. This is just a set of functions, and we can define a positive definite kernel on it. Yeah. So, okay, so we know this is a positive definite kernel, and the reason why we prove this is we know certain properties of positive definite kernels, and we will use these properties now to show that it is strictly positive definite, because if we know that it's a symmetric bilinear form, which is strictly positive definite, we actually know it's a dot product. Okay, so how do we see that? Well, let's first, let's just look at this quantity f of x squared for arbitrary x. So remember the Cauchy-Schwarz inequality, we knew how to upper bound something like this. No, actually we're going to use that later. So, but anyway, let's just look at f of x squared. And for arbitrary x, so first of all we use the fact that k represents point evaluation. So we write this as a dot product between f and k at the point x. We still have the square. Now we are going to use the Cauchy-Schwarz inequality that we have proven before. So remember, how did it look? So this is our Cauchy-Schwarz inequality. So put it into your iconic memory for a second. It looks a bit different now, because now the positive definite kernel that we are working with is this thing with angular brackets. It's not the k, even though k is also a positive definite kernel. So we use the Cauchy-Schwarz inequality, which means that this is upper bounded by the kernel of this with itself. So that's this quantity times the kernel of this with itself. That's this quantity. And so we could rewrite this as k of xx, but it doesn't matter, because the main point here is now that if this quantity here were 0, the function would actually be identically 0. So if f with f, if this angular bracket thing with itself is 0, then the element that we have substituted here is identically 0. It's a 0 vector. And that's what a dot product has to satisfy. This is the positive definiteness property of a dot product. Also positive definiteness. So therefore we know that these angular brackets actually are a valid dot product. And we're done, apart from one technical detail, which is now we have a dot product space, sometimes called pre-Hilbert space. If we complete it in the corresponding norm, so this dot product implies a norm. So this f is the squared norm of f. If we have completeness, if we complete the space in this norm, which means we add all limit points of Cauchy sequences. So effectively, if you can think of it this way, that we then also get like infinite sums of such things, then we get a Hilbert space. So Hilbert space has this nice property that all Cauchy sequences actually converge in the space. So it's a complete space. Okay, so that's the construction of the reproducing kernel Hilbert space. Do we have any questions up to here? Maybe this is a good point for a few questions. Was it too slow or too fast? So who thinks it was too slow? Who thinks it was too fast? Who thinks it was about right? Oh, thank you very much. Okay, good. So maybe I'll do some. Is your brain full now? I have a little video about La Palma that I could show at some point. But it's a bit scary, so we can also continue. Well, there's this. I once downloaded this because there's this theory. You know, La Palma is formed of two volcanoes, and there's an English geologist who has this theory that half of La Palma will one day sink into the sea and create a huge tsunami. So I find it quite interesting. I just hope it doesn't happen while we're here. But actually, I think it's more dangerous on the other side of the island. But maybe not everybody likes tsunamis and things like that.
Are we on the good part?
We're on the, if I remember correctly, we're on the right side. Yeah. So it's quite possible that if it happens, it will be more dangerous on the east coast of America than here. Although I'm not sure. It's a speculation. So why don't we say we take a 5-minute break just to walk around a bit. And I'll play this video here, but feel free to walk out, take a bit of a break. Actually, I don't have sound though.
Plug in traveling,
Are you